transforms and residuals, and we're going to focus on using the Casio class pad. And one of the things you really need to have is this called the circle of transformations. Make sure you've got a copy of that in your notes somewhere so you can see what transforms you need to use. So whenever you see a graph and you think to yourself, oh, my curve kind of looks like this, then I know I can use these 4 transforms. Or maybe my curve looks like this, then I can use these 2 transforms for that. And that's what we're going to look at today, and use the Casio class pad. So this is the data I'm going to be using in my examples today. So you probably want to pause the video about now and just tap those values into your calculator. It's very, very important if you want to learn how to use the Casio class pad. Play along at home, you know. If you don't, you won't actually get the sort of memories of this happening with you. So pause the video, get this data in, and then continue on and follow each step as we go through. So the first thing I want to do is I've got my data, I want to graph it. So I say set graph and then click setting here. And normally by default, it'll be scatter. And just double check, because if you've been using the calculator a bit, it might not be set to these. Use list 1 and list 2. So your X is list 1 and your Y is list 2. And this is where I start to say another pro tip for you to start doing is start doing this thing on a little bit of paper on the side. Just go L1 equals X and then L2 equals Y. All right, and just keep building up that list as you go through. Otherwise, you're going to lose track of things, and renaming all the lists is a bit slow. Okay, so just remember to keep your sort of idea of list 1 equals X and list 2 equals Y. And as you can see, we've got a lovely graph down the bottom, and we can definitely see it's non-linear because we can see we've got this curve here. And compare that red line, which is going closer to the dots, with the blue line, which is a straight line. And you can see that, this data is non-linear. I'm going to do some analysis of that to show it's non-linear along the way. So let's do that linear analysis. So we're going to do, we press calc, then regression, then linear reg. And we want the X is list 1. Remember we said X is list 1 and Y is list 2. And we're also going to do this. We're going to put the residual into list 3. Now what we really want to pay attention to here is this value here, the R. So we've got here that R equals minus 0.927. Just going to go to 3 significant figures. That's 3 significant figures. Don't forget to do your rounding there. And it's negative because it looks like this. So even the slope is negative, the gradient is negative. So you can see that the B is also negative. Let's just highlight the B in a negative color. If B is negative, R is negative. If B is positive, R is positive. And that's because it's to do with the gradient of the line. They're connected in that way. But what we've got to do is throughout the whole process is when we're looking at what's the best transform, we're trying to say which one has a better R. As the R gets better, we've got a better transform. Okay, so at the moment we've got this blue line down the bottom and we've got our dots, and you can see we're doing this sort of shape. Now I'm just going to do a residual analysis, and all we're doing with the residual analysis is we're just taking exactly the same graph, but this blue line, which is at an angle at the moment, we're going to make that blue line horizontal, and then you'll still be able to see the same sort of curvy line of like this. Okay, so if you just tilt your head to the side, and what we're doing is taking this blue line here and making it horizontal, and that's this list 3. Okay, so what we're going to do is we're going to say, well, hang on, let's remember ourselves. So list 1 equals X, list 2 equals Y, and list 3 equals the XY residual. All right, so this needs to be L3, and this still needs to be list 1. And so that's what the next thing we need to do is graph that. So again, we're going to set graph setting. And remember what we said, we want to actually have the Y is list 3 because list 3 is our residual. So now we'll do a graph. So before, this is the blue line we had before. Remember it was an angle and now it's straight. And you can see we've got we've got this curve like this. So remember, pattern equals non-linear, so it's not a line. Don't worry about this dude here. That's the old line. That's the equation of the line. That's the x y line we had before from these two guys. They just leave it in there for some reason on the calculator. So we want to have no pattern equals linear or good transform. Okay. So if we go back to our original data and graph, we had that sort of situation, which is a curve like that, which looks like it fits this guy. So we can do any one of these transforms. Now, imagine we've got a line, I don't imagine, I'm going to draw it. Imagine we've got a line like this. What we're saying is if this is your y-axis and this is your x-axis, we need to get these x values to go that way, which is smaller. Or we can get the y values to come down and be smaller. So shrinking y or shrinking x, and that's what we're doing. So you can see that log y and reciprocal y and log x, reciprocal x are shrinking. So I'm just gonna do these two. I mean, we could do all four, but longer video and repeating the same things. But so log of x is a shrinking function. We're going to make the x values smaller, and reciprocal x or inverse x, depending on your notebook, is also a shrink x. The opposite is over here. That's x squared, and that if you do x squared, you're actually stretching x, and that makes sense because if I did a line like this, I need the x values to get bigger to hit towards that line, whereas down the bottom here in the opposite corner, you can see that you need to stretch them. So that's what we're going to do in the next stage. Is we're going to log x and do reciprocal x and see if there are better transforms. Now the first thing I do is I'm going to put this into list 4, which means I need to click here so it all goes black. Then I click here, and I'm starting off, I'm going to do reciprocal x. So I'm doing like 1 over x. But remember what I said? So list 1 is x, list 2 equals y, and list 3 equals the x, y residual. Now I'm going into list 4, and list 4 is 1 over x. So remember to keep track of that. Do get into the good habit of doing that. And then you won't make so many errors because it's going to get messy otherwise. So here we got our list 4 values, and it might be a good time to pause and look at what's happening because there's this weird thing happening over here with these e-neg3s. So we've got the values 0.1 and 0.025 and 0.0125, which are definitely getting smaller. But let's have a look at this 6.3 e-neg3. What does that mean? Now it's going to be a smaller number, otherwise it's going to be a weird pattern. But this is exactly the same as saying 6.3 times 10 to the neg 3, which is your scientific notation. And you can write it just like that, and that'll be fine. Lovely 2 significant figures there. But what it's basically saying is we've got to take this decimal point and move it 1, 2, 3 points over here. So what you actually end up with is that equals 0.0063. And there you can see the 3 moves, 1, 2, 3. So it's here. So if I was actually to write the rest of that list out in the sort of the normal decimal places, you get 0.0063. 0.0042 and 0.0033. And now it's making sense. We can definitely see there's a pattern of decreasing, and it's all definitely every single one of them is going down. Now, another thing to note right here is that, remember, this is reciprocal of list 1, and if we look at the list 1 values here, they're not going down, they're going up, and this happens a lot. So whenever you're doing the reciprocal, remember we said we had a negative graph like this, we're actually going to have, when we do reciprocal, you're going to have a positive graph. And it always does flip like that when you're doing reciprocal. And that's going to have an interesting effect on R. So as always, calc, regression, linear reg. Okay, so we'll make sure we've got to put list 4 in here, because let's remind ourselves, list 1 equals x, list 2 equals y, list 3 equals the xy residual, and list 4 is the reciprocal x, and that's why we've got to make sure we change the x to list 4. Okay. All right, now we've got to compare our R. Now remember what we said, so when we had the xy, R was minus 0.927, things to write down. But now we've got 1 on x versus y, and our R equals 0.862. So a thing to note is this is negative, and that's what I said. Remember we said like the graph goes from this, but when you've done reciprocal, it goes to this, it becomes positive. And I told you that also B is going to be a positive value if R is a positive value. But we don't need to worry about the sign, so don't worry about the sign. We just need to look at the 0.927 and the 0.862, which is better, or which one is closest to 1, or closest to -1. And we can definitely see that although we've done a transform, this guy is still winning, so x versus y rather than reciprocal x versus y. So that's not a good transform. Abandon transform, move on to another transform. Now, we're going to try another transform. So again, we click at the bottom of list 5, and we're going to try this time logging x. Remember, that was our other transform we're going to try. So list 1 equals x, list 2 equals y, list 3 equals x, y residual. List 4 equals 1 on x, and we just said that was no good. So now we're doing list 5 equals log of x. All right. Here are our lovely values in list 5 now. And you'll notice that in this case, we're definitely expecting like as we go down the list, they're increasing, and that's exactly what happened if we saw list 1 over here. We'd see the same thing, because we are expecting a graph to be the same like that. So we're going to be checking that the R is good. So we go calc, regression, linear reg. So paying attention to list 5 now, because list 5 was log of that. And let's look at our R. So now, before we had said for x versus y, the R equaled minus 0.927, but now we've got log of x and y, and our R equals minus 0.987. Well, now let's have a look at those values. Remember, we can ignore the sign. They're the same anyway. And what we're going to focus on is 927 and 987. Which one is better? Well, this one is better because it's closer to 1. So we can say it is a better transform because the R has increased. So log x is a better transform because the R has increased. Technically, in magnitude, that's a fancy word saying I'm ignoring the sign. I'm ignoring the sign, and it's got bigger in the value, and it has. It's gone from 927 to 987, which is an increase in magnitude regardless of the sign. Now, since using list 5 for my x gave me a higher R, I haven't touched the y, so that's still in list 2. I'm going to actually copy my residual to list 6 and see what happened with a graph of that. So let's just remember, list 1 equals x, list 2 equals y, list 3 equals x, y residual. List 4 was 1 on X, which you said was no good because the R, the magnitude of R, it doesn't matter about the sign, wasn't so good. List 5 was log of X, which is why we've got it in here, and that had a very good R, so we'll give it a tick. And now we're doing it. List 6 is the log of X versus Y residual, and that's what we're doing. Now, a lot of people, when they do all these things, they assume that this graph is the graph that I want, and it's not. This is not the graph you're looking for. So just double check that these values are the ones you've got in your graph, and that they're not the values you've got in that graph at all. I mean, the first one is here is -7, and that's not even a negative, is it? So a lot of mistakes can happen if you've forgotten to change the settings on the set graph. So always double check your settings on your set graph. So settings on the set graph. And remember, we're going to have a graph like this. So our residual is list 6, and this is list 5, isn't it? Because that's, this is why you got to write down your list. That's log X, and that's the log X versus Y residual. This is why you need to make that list on the side there. It's like I know what I'm doing. So there we got list 5 and list 6 here on our settings for our set graph. Check your graph. Now, I've been emphasizing this a lot for a reason. Is that graph the graph that you think it is? Have you checked settings and set the graph? Because it could be a hangover from a previous part of a question, or even from a previous question that you did. And so you might be looking at that graph going, ugh, and there's a reason that it's causing you problems, is because, you know, if that's that negative, oh, that's negative, that's positive, that's positive. It is the graph that I want. So make sure you are looking at the graph that you want to be looking at. Now, when you have a graph of a residual, that's 0, and this is your residual here. There are two patterns. That is a pattern that you're worried about, and then this could be a pattern. And remember, pattern is bad, because pattern means you haven't got a good transform going here. But if we look here, look, we're going zigzag, zig. All right, that's not a pattern. All right, so no pattern equals linear. Now I say linear for this, but remember the equation I graphed is using list 5, and from our list 5 was actually log X. So this is actually a linear graph if your graph is of the equation y equals a plus b log of X. Let's emphasize that log of X, because that's what list 5 was doing down here. It says log of X, all right, log of list 1. All right, so this is quite good, and we like that. Why did we like that transform? Let's remind ourselves, because the R increased. So therefore, that's what those 3 dots means. Therefore, log X is a good transform. So hopefully that's clarified a few things about what you're looking at with R and what you're looking at with residuals and the patterns and stuff. And then in the next video, I'm going to look at the using the equation. So this lovely equation we have down here, this thing, I'm going to look at how to use that.